This is video 4 for chapter 20 on voltaic cells. A voltaic cell is something that is a new concept for you guys, but it's going to utilize chemistry you're already familiar with. We're going to take a reaction that we normally would consider spontaneous, and we're going to use that to actually generate some electricity so that it can perform electrical work. When we do that, it is called a voltaic or a galvanic cell. And what happens in those is that the electrons actually are transferred via an external wire, and I'll show you what that looks like in just a little bit. And we're going to use reactions you're already familiar with. So for example, you have one on your sheet right here. And in this reaction, I'm going to just rewrite this. Last year, let's say you were in first year IB Chem, you would have been told this reaction just slightly differently. You would have had zinc solid, and we would have given you something like maybe copper nitrate. And we would have asked you if that reaction even occurred. And so last year, you would have thought about what type of reaction this was, and you would have said, well, it's a single displacement reaction, I hope. And you would have known that then we need the activity series to determine whether or not this reaction will take place. So you'd use your blue sheet, your activity series, and you'd see that zinc lives higher on the blue sheet than copper does. So we would know that this reaction would occur. So we would know that zinc would take the place in the solution, and that copper would get shoved out of the reaction by itself. And you would have been doing this last year. And this is still true. Zinc reacts with copper to make zinc nitrate and copper solid. Now, how are we going to use that differently this year? Well, if you've noticed, in the reaction what I've done is I've ignored the nitrates, and I've just written everything as signs. And in doing so, it's a little bit more obvious to see what's oxidized and reduced. So let's look at our components here. In this reaction, you have zinc, a solid. And you might remember that every elemental state is assigned an oxidation state of 0. But over here on the right-hand side, it's got a +2 charge. That's what the zinc is doing. Now the copper starts at a +2, but it finishes at a 0. And so just think about this for a moment. One of these is oxidized, one of these is reduced. Reduced means the charge goes down. So the copper is reduced and the zinc is oxidized. Now what we're going to do is we're going to write the half reactions for each of these. So the oxidation half reaction is zinc, solid, making zinc ion. And then to get the charge to balance, I have to add 2 electrons to the right-hand side. Now for the copper, that's the reduction reaction. I start with copper at a +2, and I finish with copper solid. And to get this to balance, I have to add 2 electrons to this. Now, last year, we would have said the reaction happened because zinc was higher on the activity series, and that is true. But the reason that zinc is higher on the activity series is because zinc is more easily oxidized than copper. So we would say that zinc is a better reducing agent than copper is. So again, remember the activity series you learned last year. The things that are at the top are very good reducing agents because they are easily oxidized. Now, how does this work to put it into a voltaic cell? Well, if you flip to the next page, you'll see this diagram. And I'm going to kind of label the parts of the diagram as we go so that hopefully this will make sense to you. Now, let's go back to our half reactions for a second. Oxidation occurs in one of these compartments. And we give the names of the electrodes. They're either the anode or the cathode. Now, oxidation always occurs at the anode. And I remember, I'm sure my chemistry teacher gave us this hint when I was in high school. The way to remember that is oxidation starts with the letter O, anode starts with the letter A, and both of those letters are vowels. So remember, oxidation at the anode. And then the reduction occurs at the cathode. So reduction occurs at the cathode. And again, You can remember that because both R and C are consonants, and so reduction occurs at the cathode. Hopefully that'll help you remember that. So if we look at our diagram, now I realize you don't have the color coding like I do on the picture, but we know that this reddish brown metal is our copper. So I'm going to label this metal as copper, and we know that that copper is the cathode. And so this whole compartment, this whole beaker, is kind of what we refer to as the cathodic compartment, but the copper itself is really the cathode. And the zinc, which is what this metal is, that's zinc solid. This occurs at the anode, or that is the anode, excuse me, and this, we would refer to this as the anodic compartment. Now you'll notice this is a different reaction. Normally we would have stuck zinc metal into a copper solution, and we've separated these. Now, that's what makes it actually a galvanic cell, is the separation. So let's go through the parts of this cell. The first thing you see here is it says a salt bridge, or a porous barrier, is used to complete the circuit. So this upside down U-shaped tube is our salt bridge. So when you want to, on your diagram, you want to label this. This is the salt bridge, and it serves a purpose. The purpose of the salt bridge is to actually allow the two beakers, the solutions in the two beakers, to connect. So there's some cotton in here, but the solutions can travel through the U-tube. The U-tube itself is not empty. It has some salt solution in it. Now, there are ions moving through the salt bridge, and the cations are moving towards the cathode, and the anions are moving towards the anode. And they're moving inside that salt bridge. So there's one set of diagrams there. The salt bridge is hopefully now labeled. The second bullet point says that the solid metals are the actual electrodes. So the zinc solid is the anode, the copper solid is the cathode, and electrons flow from the anode to cathode. So the anode is negatively charged, and the cathode is positively charged. Sorry for that delay. I guess hopefully you guys can label that yourselves a little bit more clearly. There we go. All right. Now, electrons can flow from the anode to the cathode, but they cannot flow through the solution. So they have to be transported through an external wire. So up here you just see this black little wire that's connected, and this is where the electrons are moving. And electrons are going to generate from the negative and travel towards the positive, because opposites attract. So this right here is what we call a voltmeter, and that will register the voltage that's provided by this reaction. In this particular reaction, the voltage is 1.10 volts, and we'll learn in our next video where that comes from, but right now just sort of take it on faith that it is 1.10 volts. So we could use a voltmeter measure to measure our volts there. Okay. What else do we need to talk about? We already talked about anions and cations moving through the salt bridge. And the way I remembered that when I was learning is just think of them moving home. Cations are going towards the cathode, anions are moving towards the anode. Okay, so those are all the parts of your voltaic cell. So hopefully your diagram is a little bit now more labeled than it was before. The only thing that's missing is that there is clearly solutions in each of these beakers, and there's a solution in the salt bridge. So I'm going to just finish off by labeling this. Usually you put the metals in a solution that they are part of. So for example, zinc would sit in zinc nitrate aqueous. And copper, you can tell that that's kind of a blue solution on the screen. Copper sits in a copper nitrate solution. And there could be any salt solution in this salt bridge. Let's just say for argument that it's NaCl aqueous. It's just some salt solution that allows for cations and anions to move. Okay, so what we're going to do next is we're actually going to watch a video of a Voltaic cell. Maybe.
When a strip of zinc metal is immersed in an aqueous copper-2 sulfate solution, electrons are transferred from zinc to the copper-2 ions. Copper metal deposits on the zinc strip and collects at the bottom of the flask. Zinc atoms are oxidized to zinc-2 ions, which enter the solution. This spontaneous oxidation-reduction reaction is summarized in the chemical equation shown. The spontaneous copper-zinc oxidation-reduction reaction can be made to yield useful electrical work by incorporating it in a Voltaic cell. The zinc electrode is immersed in a solution of zinc sulfate. The copper electrode is immersed in a solution of copper-2 sulfate. No current flows through the light bulb because the electrical circuit is not complete. To complete the electrical circuit, we add a tubular bridge filled with aqueous sodium sulfate solution with a porous plug on each end. We now have a complete circuit and current flows. When we replace the light bulb with a voltmeter, we find that the cell has a potential for voltage of 1.1 volts. The copper electrode is the positive electrode, and the zinc electrode is the negative electrode. As the cell reaction proceeds, zinc atoms of the zinc electrode lose electrons and move into the solution as zinc ions. At the same time, copper-2 ions acquire electrons at the copper electrode and form copper metal. The reaction in the left-hand compartment is oxidation of zinc. The electrode at which oxidation occurs is called the anode. The reaction in the right-hand compartment is reduction of copper. The electrode at which reduction occurs is called the cathode. Electrons flow from the anode to the cathode through the external circuit. To maintain electrical neutrality in the two cell compartments, ions must move through the salt bridge. In summary, remember that in a Voltaic cell, the anode at which oxidation occurs is the negative electrode. The cathode at which reduction occurs is the positive electrode. Electrons flow through the external circuit from anode to cathode.
All right, so going back to our diagram, you'll notice that in the video, the example they used sulfate solutions instead of nitrates. Again, that part isn't that important. What is important is that you put zinc in a solution that it contains zinc, and you put copper in a solution that contains copper. That's the important part. So I know this diagram looks overwhelming, but really it's if you break it down into each piece, you probably can get through it pretty quickly. So that's what a Voltaic cell is, and in the next video, you should learn how to be able to calculate the voltage of the Voltaic cell.